Okay, good afternoon. Let's continue with our discussion on the capacitances, right? So last class we concluded by discussing about the capacitances of various nodes in a NAND gate, right? And we discussed the concept of a shared uncontacted diffusion versus a shared contacted diffusion, right? So if you had a NAND gate like this, right, size 2, 2, 2 and 2, right, then the net capacitance here would be 6C, 2C coming from each of the two PMOSs, right, and one 2C coming from the NMOS on top. The intermediate node would have a capacitance of only 2C as opposed to 4C because this is a shared uncontacted diffusion node, right. So this is a uncontacted diffusion. Whereas if you look at the two PMOS transistors, even though the drains of both PMOS transistors, drain 1 and drain 2 are shorted, they are a contacted diffusion and therefore you need more space. So effectively the capacitance goes up because of that reason. It's not like you have just one diffusion there for both these transistors. There are two diffusions and you have to have sufficient space to connect these two diffusions together with a metal, and therefore this will basically be a shared contacted right, and therefore each of the nodes will contribute to a capacitance of W into C. Clear? So now let's go ahead and use this concept to figure out what the capacitances of a NOR, let's say a NOR 3 gate straight away, right. So first, can you sketch a NOR 3? Y equals A plus B plus C whole bar. So how many transistors on the PMOS stack? It's a 3 stack thing, right? So yeah, A, B, C, A, B, C, right. So what are the sizes of the NMOS transistors? 1, 1, 1, right, because the worst case is only one of them turning on. PMOS 6, 6 and 6, right? So this is 6, 6 and 6. So remember I told you that the resistance of a PMOS transistor with width W will be 2R by 6, 2R by W, right? The normalized resistance will be 2R by W, and therefore this will be R by 3, and you add 3 of them, you will get a net resistance of R on the pull-up path as well. So what are the capacitances now at various nodes? What is this capacitance? From the NMOS, how much, what is the capacitance? Huh? 3C, right? From the PMOS, how much of capacitance will you get from the PMOS? 6C. So this is 9C. Now what kind of a node is this? Node X, node Y? Shared uncontacted diffusion again. So therefore I can put a capacitance of how much? 6C here. Similarly Y, another 6C. Okay. So remember that this shared contacted diffusion, only in this NAND and NOR case, simple cases, it's easy to figure out without doing the layout. Otherwise you have to go into the layout to figure out what happens. Okay, so we are not worried about those things right now, in the sense that ultimately when you do a simulation with the layout extracted netlist, you will get all that information appropriately, right? But it's not easy to always say that if I give you any arbitrary circuit, how many of them will be shared uncontacted or how many of them will be shared contacted diffusions. That depends on how you lay them out, right? And it can vary from person to person. There will be multiple ways of doing it also, right? So this is just something to keep in mind, where when there is clearly a shared uncontacted diffusion, don't double count the capacitance. That's a very reasonable approximation, and it's also valid in reality, right? But it's not easily extendable to every single case of layout that we do. Okay? Okay, right. So with that, we can now start calculating delay of logic gates. Okay, so let's start with a simple NAND 2 example. I want to calculate rise and fall delay. Okay. Now, sorry. In each rise and fall, there are two kinds of delays that we will see: the worst case delay and the best case delay. Okay. Why is that? Because, for example, if you take the rise delay, only one transistor pulling up the output would be the worst case delay, right? If this happens, then it happens through a resistance of R, and therefore that is going to be your worst case delay. On the other hand, if it gets pulled up by both transistors together, then it's an R by 2 resistance, and therefore that's your best case delay, right? So the definition of these two delays is, I have, for each of these two, I have something known as propagation delay and contamination delay. So this is your worst case delay. This is your best case delay. Contamination has a negative connotation to it because in sequential circuits, contamination delay can actually affect your circuit quite significantly because data can race through the gate and go and affect your flop in the next stage, right? While the flop is trying to capture data of this particular state, data of the next state can just race through and go and contaminate that flop, and therefore it has a negative connotation to it. It's called contamination delay, right? That's all. But just keep these two in mind for now. So now I want you to calculate rise propagation, rise fall delay. I mean rise propagation, rise contamination, fall propagation, fall contamination delay. Okay, so let's start with rise propagation delay. So what's the equivalent RC circuit first for this? Yeah, rise propagation delay. Yeah, there is just one resistance R, right? Our size of course is 2, 2, 2 and 2, right? Then there is a capacitance which has to charge up. And what is that capacitance value at the output node? Yeah, 6C, right? So the delay is how much? 6 into RC, right? What about rise contamination delay? What's the resistance? Yeah, so I'll write this explicitly. Both resistances turn on, 6C. You will get what? 3RC as my delay. So now let's come to the fall delay. Fall delay propagation. Okay, so I have my output or maybe I should start with contamination delay. What's the case for contamination delay? Louder, I can't hear. Okay, I just can't hear today, maybe because I'm little down. But so the bottom transistor, suppose that input was high for long enough and it has discharged that intermediate node X to ground already, right? Then the output Y needs to be pulled down to ground, that's all. As opposed to if the A input also had to discharge the input X to ground, then it's both these nodes that have to be discharged to ground at some point. So therefore the contamination delay is right fall contamination delay. Input A is high for long, right? And discharged node X Therefore, if you look at the equivalent RC circuit, you have the node Y with a capacitance of 6C. You have a resistance of how much? How much? R by 2. NMOS size is 2, right? R by 2. 2C is the intermediate node capacitance, but that has already been discharged to ground, right? So therefore, if you remember this problem I gave in the quiz, where one of the nodes was already discharged slightly, then you apply that condition and that thing will just vanish out. That capacitance will vanish, okay? It doesn't mean that the resistance will vanish. That's the key point here. The current still needs to go through that bottom NMOS transistor connected to A, and that still offers a resistance. It is just that the capacitance has already been discharged, okay? And therefore the net delay will be 6C into R by 2 plus R by 2. 6 RC, right? You apply the same thing that I gave in the quiz. Initial condition where instead of 3 by 4 VDD, I said so you make that ground. That term will just vanish. That capacitance term will just vanish, right? But the on path resistances will still come for the other guys, correct? And therefore that becomes 6 RC, okay? For propagation delay, both X and Y need to discharge to ground. Right? So what's the equivalent circuit? I have here, I think I should write this. Vc of 0 minus equals 0. Yes. True. So that's where the approximation that we made for this Elmore delay model comes in. It is true that this node, for it to accommodate some current, will actually bump up slightly. So this is only an approximate answer. It's not an exact answer. That node has to bump up slightly to allow some current, and therefore you will have some charging of this capacitor also slightly in the process and all that stuff. So those are second order effects. The first order effect is you can neglect that and you will have 6 RC. The fact is contamination delay is lesser than the propagation delay in these two conditions. As I told you, you can check it out through simulations. It may not be exact, that's all. Okay. So her question was, if this capacitance was already discharged to ground, that means the VDS of that bottom NMOS transistor is 0. So how can you have any current flowing through that? So she is right, because to accommodate some current, the VDS has to bump a little bit, right? Only then you can have some current. So, but that becomes a second order effect, right? So in the Elmore delay approximations we made, we said that everything falls as VDD e power minus t by RC, right? So those approximations are, those are only approximations, right? So you can go check it out in simulation for yourself, but to a first order, this is a reasonable approximation to make, okay? So node Y, capacitance is 6C. I have a resistance of R by 2, 2C, R by 2. So what is the delay? What's the answer? 7 RC, right? The Elmore delay model you use, you'll get 7 RC as the answer. Sorry. So can you work out for a NOR 3 gate now? The NOR 3 gate, only the propagation delays. Yeah. So what's the answer? Rise delay 15 RC, right? Which is 9 into 6 into 2R by 3. So 2R by 3, 4, and yeah, 15 RC. And fall delay 9 RC. That is very simple because it's just this and 9C, and this will be R. 9RC is the thing. What about contamination delay? Rise is just 9RC, is it? Correct, exactly. And fall 3RC. Okay.